So, welcome everybody. I'm afraid that the lunch took a little bit more time than expected, so however the program has to go on. So I will briefly introduce our speakers, and since we are already a little bit behind with respect to the schedule, I will skip part of a few things I was going to say about IEEE CEDA, who is actually hosting this keynote at lunch. And the council was founded more than 20 years ago, so I hope that sooner or later there will be a chance to get to know us better. There is the URL of the website, so I hope that you can go there and gather the most relevant information about the council, who is the network and the joining point for electronic design, automation, research, education, and connection and networking. I don't want to steal more time from our speaker, who is, let me wear my glasses, otherwise it will be difficult to create a new biography for our speaker. Zhiru Zhang, who is a professor from Cornell University. And he also serves as the lead PI for the heterogeneous computing platforms themes in the SRC DARPA JUMP 2.0 ACE Center for Evolvable Computing. Let me go to saying that prior to joining Cornell, he co-founded AutoESL, a high-level synthesis startup, and later acquired by Xilinx, now part of AMD. And AutoESL's HLS tool evolved into the Vivado HLS, and now VT's HLS, and is widely used to design FPGA-based hardware accelerator. He is the receiver of plenty awards that I don't have the time to mention, but I want to leave you immediately the floor to you. Let me start your presentation. And here we are. Thank you very much.
Okay, thank you very much, Christina. I really appreciate the opportunity, for the invitation from CEDA, and also the opportunity, to present some of our recent research on unifying the abstraction for the accelerator design and programming. And actually, our goal is to make the computer systems much more evolvable. Okay, speaking of evolvability, I'm sure that the audience here is quite familiar with how the digital computing has been evolving in recent years, right? Basically 2 decades ago, denar scaling ended, so that's where we stopped getting some of the free benefits, right, in performance, right? So we see the clock frequency scaling. So that's where the whole field had no choice but to go to the multi-core CPUs, and also back then the general purpose GPUs also started to emerge, right? So that's where we basically have to go parallel and also go spatial, right? The thing is, with this hatchet, I think there's some echo. Just make sure that I'm okay, right? So is there any echo? Okay, all right, good. All right. Sorry about that. I was just talking about this general purpose, the multi-core architectures. In many cases, they're actually not efficient enough, right? Especially in terms of the energy use. So that's where we are starting to embrace this heterogeneous architectures by incorporating some of these domain-specific, also application-specific hardware, right? AKA the accelerators. And actually these days, right, to better deal with the memory bandwidth limitation and also further increase the efficiency. So we want these compute units to grab data from nearby as much as we can, right? So that's where we are seeing more of these data flow approaches, right, emerging, and also we are pushing towards this near and also in-memory processing. So as a result, right, so this really leads to where we are, right? We are firmly in this age of accelerator-rich computing. We are building many of these accelerators, right, for both the data center and also for the edge. But there are some challenges, right? There are actually some major challenges to accelerator-rich computing, especially in terms of the evolvability. So the thing is, we actually know very well that these accelerators, they are actually optimized for hot domains, especially AI, right? But if you look at these AI workloads, they sort of constantly change, they constantly mutate, right? With this sort of new sparsity trick, new models, also new quantization techniques. But with the current design methodologies, in many cases, right, the hardware innovation is just too slow to keep up, right? So, at the same time, so if you look at the software side, right, actually we need, in many cases, we actually need to build a specialized software stack for each new accelerator instance, and in some cases, even for a new accelerator upgrade. So that requires a large specialized development team. So the thing is, so with all of this, right, so currently the accelerator development is just still too slow. Of course, with the rise of AI, the natural question to ask is, can agentic AI help? Actually, they can do many things, right? Many useful things. They can, write code, right, including HDL. They can set up environments. They can run tests, right? They can actually organize findings and do analysis. Many wonderful things. But we also know that, look at this agentic AI. So their performance sort of largely depends on not just the reasoning power, and also how fast we can iterate, right? How fast we can propose, right, refine, and then test, okay, and evaluate. But if you look at this pipeline, right, so there's clearly a bottleneck, right? So with the current AI, even with the current AI, the CAD tools are still pretty slow. We cannot make them run faster, right? Especially with place and route, right? So also with RTL level design, still very slow. And worse, so for each new accelerator instance, so we still need to build this software stack. Currently, AI cannot do it, at least not yet. Okay. So to address these challenges, we actually have a pretty bold vision. We really want to make sure that the hardware accelerator sort of co-evolve with the software. Okay. So which means that we want the accelerators, right, to be automatically generated from software. And also, at the same time, we want to quickly bring up the software stack, which is crucial. Okay. So to really achieve this vision, so I argue that it's critical, it's actually essential to unify the abstraction of accelerator design and also accelerator programming. Okay. And also, we want to leverage modern AI systems as much as we can, both the AI software, the models, and also the AI hardware. Okay. All right, so I'm going to cover both aspects, right? But for this talk, I'm going to focus more on the first one, the unifying the abstraction. When I say unifying the abstraction for accelerator design, also programming, some of you may ask, right? So aren't they sort of apples and oranges? Okay, so indeed, right? If you actually look at the current landscape, of the accelerator design, also programming, they are actually very much disjoint. Okay? On the programming side, in the interest of time, let's just focus on AI hardware, right? So right now, it's actually largely dominated by something called SPMD, the programming model. A single program, multiple data. Right? So the CUDA, right, Triton, like OpenCL. So those are the prime examples of SPMD. So there, the mental model is basically, we have many sort of largely independent threads, so which are running over a grid. Okay, so this is the mental model for SPMD. On the design side, the mainstream design entry is still RTL, right? Still HDL. Okay, so there, basically we have to explicitly, create the FSM, also data paths, right, to infer, this accelerator architecture, so which is fairly low level. Of course, there's also HLS, right, which is gaining, adoption. So with HLS, at least with the current mainstream HLS tools, it's still, mostly based on C or C++. So where the designer needs to basically infer the pipeline and parallel data paths from sequential loop nest, and also by inserting pragmas. So this is the current, the design methodology using HLS. Of course, these days, right? So many of you may ask, right? So what about vibe coding? So can we again, leverage agentic AI? Like I just mentioned, right? So even with vibe coding, I think it's going to be really useful, right? To have a clean abstraction, so that we don't have to work at the low level like RTL to speed up the iterations and also to minimize the token cost. And also, we actually want to ease the verification, right, as well. Okay, so this is something that I may talk about. All right. So this is sort of where we are, the lay of the land. Let's take a closer look at HLS. Since I've been working on HLS for a long time, I got to say a bit more things about this. Actually, with the current HLS tools, they are pretty good at a subset of problems, especially for creating these this custom application-specific pipeline, especially targeting FPGA. So that's where you can just write a loop nest and either pragmas and say pipeline. You can actually write fairly complex programs, right? Release multiple loops and also multiple functions. You can still get to create something in a productive way. Although you may lose some performance, but the effort is not too bad. So it's actually worth the trade-off. But on the other hand, the HRs, the adoption is somewhat limited for building these more structurally regular and domain-specific hardware. Actually, there, in many cases, the effort of designing at HR's level is, not much lower than just using the RTL. Okay? Just to draw imprecise analogies, to some extent, logic synthesis is dealing with similar issues, right? So logic synthesis is actually less effective on the more regular arithmetic block. Okay? It's actually more effective on the random logic. Right, so let's, this might be a bit abstract, but let me just show you a concrete example. So here's a 2x2 system array. Okay, this is structurally regular, very intuitive, right? Very sort of easy to reason about for a human designer. But if you look at the HR's code over there, it's actually surprisingly convoluted, right? So that's where we have to actually encode this parallel and structured architecture in this sequential code, and hoping that the compiler can infer them back. Okay. So that's where we actually spend a lot of time massaging the code, inserting pragmas. So in the end, even for a simple systolic array like this, so we actually need more than 500 lines of code in C++. So which is right, which is quite a bit. But the thing is, if you think about this, right, if you think about systolic array, right, this structure. Also think about many of these domain-specific accelerators, actually in general for accelerators. So we are basically hardening a specific compute pattern, right? Whether it is application-specific or domain-specific, so in hardware. And then we achieve high performance by replicating them. So this is really the name of the game, right, for hardware acceleration. So that means there is some intrinsic regularity in the architecture. So in this case, okay, over here, right, so this is already, this is fairly regular, right, also spatially scalable. So that's where, naturally, so we can use a grid-based representation to capture this, right? So for example, over here, we can, for each component, we can just assign a grid point, a coordinate, okay? And just capture the whole thing, right, in a clean fashion. So that means, does that mean that SPMD is the answer? Okay, so that's the sort of natural question. The thing is not quite, right? Actually, there are some existing attempts using OpenCL for HLS without widespread success. The thing is, the challenge is that, for these architectures, right, in many cases, these compute units, they are actually tightly integrated, right? So it's not just, we are not just dealing with, a set of, independent threads, right, like SPMD. So that's the challenge. But, at least, so hopefully from here, it's clear that there's some interesting opportunity, right, to generalize from SPMD, so that we can handle this regularity, right, in a much better way. So this is actually what we are trying to do. So we are trying to solve this, right, using a new abstraction. So this is actually implemented in a framework called Allo. Allo is actually a dual-purpose framework which can do both accelerator design and also programming. Allo has a Python front end. And also, it comes with an MLIR-based compiler. We actually released the whole framework in open source format, less than 2 years ago. We actually are seeing a growing, set of a growing user base. We are also seeing a growing number of contributors as well from both the academia and also industry. So with Allo, so what we are trying to do is, we are trying to make this accelerator design process, composable and also verifiable. And also, we really want to make this regularity a first-class abstraction. Okay. So that's where we introduced the latest version of Allo. Introduce something called SPMW, okay, which is something that I'm gonna explain. So pretty soon. So basically, the hope is that we can bridge the gap between the accelerator programming and design. Okay. And the initial the result of Allo was actually published 2 years ago at PLDI. So back then, we focused more on the traditional, HR-style behavior design. And this has actually evolved quite a bit. So what exactly is SPMW? So it stands for single program, multiple connected work units. So that's the acronym. Okay? Of course, the units in some cases may not be connected. If they are largely independent, that's also good. Okay? So here's how we represent a systolic array. Okay, let me just find the cursor. Okay, over here, this is the program. Again, we model the whole thing as a 2D grid, and then we can get the work ID for each grid point. And depending on the coordinate, we can specify different behaviors over here. So we can specify the behavior of the peripheral logic, and also we can specify the behavior of the core processing units. Okay, in this case, the PE. Okay. And right, again, there's a single program to capture many work units. And the key thing is that we also specify the connectivity between the work units in a type-safe fashion. So we actually have a built-in type system, right? In this case, to support streaming, right, between the work units, between the PEs. Now, I'm not going to bore you with the operational semantics, right? The low-level detail here. But the key thing is, with this type system, we can actually quickly check at the compile time some of the common mistake, right? Like deadlock and also some of the mismatch data access patterns. Hopefully, by looking at this program, right, you agree with me that at least the syntax looks somewhat clean, right? It's concise. But the thing is, with this SPMW, it's not just syntactic sugar. So that's something that I want to argue. It's not just about compressing the code. Actually, we can compress the code in many different ways. Now, we can just use even the in Verilog, we can use a general statement, right? We can use template in C++. But so those meta programming tricks will still sort of blow up the IR eventually at the compiler level. So with SPMW, we actually want to directly encode this regularity in a clean way at the IR level, in the internal representation as well. Okay? So that's going to enable many interesting and aggressive compiler optimization and also analysis. And also, we actually want to explicitly sort of decouple the compute from the communication. So we have this explicit specification of the connectivity, right, with SPMW. So over here, we are using stream, right, to describe the sort of the point-to-point connection. But in general, this can be a NOC, a network on chip. Right? This can be a shared memory as well, okay, communication. So that's actually flexible. But this is going to simplify typing, verification, and also physical design. And this is also not going to be just a uniform, flat grid. The grid can be heterogeneous. The grid can also compose in a hierarchical way. Okay, so to enable this composable design. All right. And also, by doing this SPMW, we actually sort of bridge the gap between the accelerator programming and the design quite a bit, so that the techniques from different domains, also ideas from different domains, can more easily transfer. Okay, so this is one of the also key benefits. All right, so let me just show you some examples. Right, of course, we can model more than just sort of a mesh or a systolic array. We can also do FFT. So if you look at FFT, in this case, there's a radix 2 FFT. We can also use a grid-based abstraction to model that. Right? In this case, two-dimensional, so the number of stages, right, and also based on the number of work units, based on the number of butterfly units. Again, in a fairly clean way. So if you look at the syntax there. Let me just show you some results. Okay, somehow this is blurred. Hopefully you can see the numbers. Okay, over here, so this is ours, right? SPMW. We are comparing the result that we generate, with the state-of-the-art HOS result, the library, and also the RTL generators from both academia, also the commercial tools. So, with this abstraction, so we are able to reduce the number of the lines, the line count, by a factor of 10 easily. But the better news is that we can also improve the design quality, because with this new abstraction, we can actually do pretty interesting data layout optimization automatically while we are folding the grid for research sharing. So that's where we adapt some techniques from the recent GPU compiler papers. Okay? This is from Asphalt 26 paper, so we are able to adapt that, also generalize that for accelerator design. So with that, we are able to improve both the line count and also the latency by almost a factor of 2. Okay? So this is sort of the power of the new abstraction. Okay, I also talk about physical design, right? Actually, these days, right, if we look at when we implement accelerator, in many cases, we are bottlenecked by the place and route, right? It's just so slow. The thing is, it's just most of the CAD tools also do not have regularity in mind. But if you can actually take advantage of that, we can dramatically speed up the whole process. So in this case, it's basically a 4x4 scissor array. Since we actually know the regular structures, we can just pre-compile the patterns, right? So in this case, a 2x2 block, okay, as a pre-placed building block. And then we just need to stitch them together. So in this case, we're using the open source tool from AMD called Rapid Write, so to do the stitching. So again, the benefit is actually pretty dramatic. So in this case, we actually place and route the whole thing flat. We need 20 minutes on a single SLR on the FPGA. But you can do this in a bottom-up fashion by leveraging the regularity. So we can cut the whole compile time by a factor of 10. So we are actually down to just 2 minutes, less than 2 minutes. We're actually developing a end-to-end flow for this. So I actually think that this potentially can be a real game changer, right, for accelerator development on FPGA. And the same idea also applies to ASIC. All right. I just talked about this structure approach, right, SPMW. We can actually also handle the behavioral style as well. This is where we can still have the user to write loop-based code, and there they just need to use a set of decoupled primitives to specify how they want to optimize the design. Again, in a fairly clean way. So this is where some of the HRS experts, so they may still prefer to use sort of the loopy code plus some basically this is sort of like a decoupled pragmas, right? Again, to quickly specify how they want to pipeline, also parallelize their architecture. Okay. All right. So far I have only shown you some kernel code, right? Actually, if you look at the literature, there are actually quite a few different papers, right? Different domain-specific languages, right? So targeting this area, but also mostly they just focus on single kernel design. But Allo is actually different. We actually want to have strong composability so that we can easily compose different kernels, right, to build something much more complex. Okay, let me just show you some examples. Actually, we can do this in a type-safe fashion as well. So here's an application-specific accelerator. So this is a complete GPT-2 inference engine. We actually did this 2 years ago. So back then, GPT-2 is still was the only open GPT model, right, from OpenAI. So that's why we look at that. So this is the architecture that we came up with. The whole thing specified in Allo. So we only actually need just 50 lines of customization code. Over here, this is again application specific. This is the streaming architecture. So each one of these multiply is not just a single MAC or multiply addition unit, accumulate units. It's actually entire systolic array, each multiply here. Okay. We are able to implement the whole thing right on the FPGA. With KV caching, we can do prefill, we can do decode and everything. So we also compare with some of the state-of-the-art accelerator on the FPGA. So for the prefills there we are easily 2x better. Even against GPU. So in this case, A100 GPU. So for the decode stage, which is more memory bound, because we are able to implement this highly specialized architecture, we are actually able to minimize a lot of memory traffic. So that's where we got almost 2x speed up right, on long output sequences, and also much higher energy efficiency, even compared to GPU. So in this case, actually FPGA is fabricated with a less advanced process. Right? This is really 16 nanometer versus 7 nanometer, and even the bandwidth. If you look at the bandwidth there, it's also much lower compared to A100. But still, we are able to get the speed up because of the customization. Right? So this is the application-specific accelerator. We can actually go beyond that. I already mentioned that we actually want to support the domain-specific ones as well. Right? So this is something that we recently built. So we look at accelerator from our collaborator, Professor Tusha Krishna's group at Georgia Tech. So this is the Tensor DSA, or domain-specific accelerator. This one has some novel features. You can actually do this code switching of data flow and data layouts. Has two parts. One's called Nest. So this is basically a compute engines. And over there, that's the more interesting part of the accelerator. So there, this is a sort of on-chip network, which can do the data reduction and also the data reordering right, at the same time. Okay? And it's a pretty interesting architecture. We look at that, and we actually implement the whole thing in Allo. Actually, just in less than 200 lines of code. So over here, we are showing that we can sort of compose these two parts. So the first part, this kind of nest with the compute engine, we can just write the loop-style code. Okay, again, in a fairly clean way. And on the right, so that's the on-chip network, the reduction network. So that whole thing can be easily specified using this SPMW style, the programming. And if you look at the results, okay, we compare with their manual RTL implementation. It's actually done by a grad student. So I don't want to read too much into the comparison since this is not super optimized. I just want to show that the performance is actually pretty decent. Okay, in terms of the line count, right, it's 10x lower. Performance pretty much the same, with lower area usage as well. Right? Okay. And actually on top of this, so again, this is a domain-specific accelerator. Just generating hardware itself is actually not sufficient. So we are also, trying to automate the compiler stack generation as well. So that's where we are working with our colleagues, Charles Mendes at UIUC and also Tulsa Group at Georgia Tech. We are looking at how to start from Allo. We want to not just generate the accelerator architecture, we also want to generate the compiler backend in an automated fashion as well. Okay, so that's where we are leveraging the tool called ACT or ACT from UIUC. From Allo, we basically generate the hardware design and also the instruction set specification. So then we can automatically generate the compiler, the code gen, so right as well. So this is some ongoing work. We already have promising results on this feather accelerator that I just talked about. We have also designed fairly still not comprehensive enough, but fairly functional mini TPU using Allo. So again, with not just the hardware part and also with the compiler stack, all automatically generated. Okay, so I've been mostly focusing on accelerator design, right? So with Allo, I also talk about accelerator programming, right? The thing is, if you look at some of these emerging data flow accelerators, right? So even SPMD is no longer the best fit because of some of these tight interconnection, right, between the compute units. Right, over here, this is one good example. This is from AMD, right? This is NPU. This is based on the AI architecture. So there are also other examples. For example, the one from Cerebras, WSE. All of these are good examples of the data flow accelerator. There are more, right, from IBM and Semanova, Tenstorrent. Okay, there are many architectures like this. And actually, even for GPUs, so they are increasingly adopting this sort of asynchronous data flow style execution. Okay, by using something called the warp specialization. So this is for NVIDIA, and also there's this similar concept called warp group specialization from AMD. Okay, so let me just quickly show you that we can also extend SPMW for the data flow accelerator programming as well. So this is where again we use Allo. Okay, this is where we are using Allo to specify the flash attention kernel. So we still use the grid-based abstraction to specify the data flow connections. We also can specify the data layout in a clean way, and we are able to map the whole thing, right? So on this AMD NPU, okay, and we are actually able to outperform the vendor tool. In this case, the AMD Iron tool. So in terms of both the line count, the productivity, and also the performance, the efficiency. Okay, in terms of the latency. Okay, this actually turns out to be also a pretty strong fit, right, for programming the data flow accelerator. But what about GPUs? Okay, oops. Okay, what about GPUs? Right? Is it much easier to program? Right, you would think so, right? Because unless for these days, right, you hope that you expect that you can easily start with a vanilla matrix multiply kernel like this and automatically compile to this GPU, right? So for example, if you want to port a kernel from from A100 to a more recent device like H100, you would expect that the whole thing is fully automated. The thing is, it's actually not. So under the hood, there's actually a 1,000-line small bits, right, hidden behind the scene. So written in CUDA. Because over there, so if you actually want to leverage some of the new features in H100, like the tensor core, you want to fully utilize those, you have to manually transform the code and then do a lot of different optimization, like warp substitution, like asynchronous load, and MME pipelining, everything. So that you can make the best use of the tensor core. And these days, if you look at the table, the tensor core actually accounts for most of the the throughput these days, right, for the more recent GPU. So what exactly, right? Some of you, in case you are not familiar with some of these concepts, like warp specialization. So let me just quickly show you an example, right, to explain the concept. Over here, this is an example with a dot product, right? We are basically doing loading A and B, and then we do the inner product. So on a traditional GPU, so everything is actually synchronously executed. So meaning that all the warps, right, they have the same instruction stream, right? So then we basically have the CUDA core to issue the data loading and also wait for the load to process. And then we have the tensor core to continue to do the actual compute before we launch the next batch. Okay? You can see that there's actually a lot of idle time, right, which is not efficient at all. So with some of these new GPU features, right, starting from Hopper, there's a new TMA, right, engine. TMA means the tensor memory accelerator. So with these new hardware and also the new print models, so we are able to do things in a more asynchronous way. So over here, so instead of having all the warps, right, so doing the same thing, now we have more dedicated warp groups. So something that can handle just the issuing the data loading request. So we call this warp group producer. And we also have dedicated consumer warp group to just do the compute. And we have the TMA, actually to handle the real data loading, to handle the address translation and everything. Okay. So in this case, the whole latency is much shortened. Basically the whole efficiency is also much improved. Okay. But if you look at this, this is really breaking away from the traditional the SIMT style, right? Single instruction, multi-thread, but everything execute in a lockstep, right? This is the paradigm. So it's really, even GPU is entering this sort of asynchronous data flow style execution. So with all of these, new language construct and also the new hardware engines. But the problem is that, this is not easy to manage, right? From the software level, this is where we end up using these many lines of CUDA code, just to do the coordination of the warp groups, right? In some cases, we even have to go down to the PTX level, not even CUDA, to handle the low-level communication and also resource allocation and everything. Okay, it's actually fairly messy. So that's where we also try to come up with a clean abstraction. Right? Actually, in this case, like I said, right, this is very much data flow style execution. So this is where we're able to propose a new type generic IR abstraction. Okay. Where we just need to use the simple put and get semantics to handle this sort of communication between the consumer group and also producer group. Okay. And also, we are able to fully automate the partitioning of the code to generate the warps, the specialized warps, and we are able to actually match the performance, of this the handwritten the manual library, from NVIDIA, and also we are able to outperform the Triton compiler. Okay, so with a higher, right, the throughput. Actually, the whole thing is already upstream to the Triton GitHub, the main branch. This is actually joint work with NVIDIA. So this is published at CGO a couple months ago. Like I said, everything is open source. So this is Tava. Okay, so so far I have covered Allo, right, and Tava. So both of them actually make it easier to build and program these accelerators. Okay. But the thing is, this compiler itself is still largely manually constructed, right? Both the Tava compiler and also the Allo, both make use of MLIR. But can we further automate this? Right, that's the next question. Can we actually leverage the modern AI systems to further simplify the whole development? So that's where we collaborated with Google and also Google DeepMind. And we are looking at, can we make use of LLMs, right? Can we make use of the coding agents to automatically improve and also evolve this compiler optimization process? So in this case, we are looking at, we use the alpha evolve. Okay? We actually build a two-stage pipeline. So with alpha evolve and also with a Google Auto Tuner, so called the Vizier. We are basically building an autonomous loop to automatically improve the compiler process. So where the Alpha Evolve proposed a high-level policy design space, and we use Auto Tuner to automatically search within this parameter space. And the results are actually pretty promising. So we are able to see improvements on a number of important compiler optimization process. Also, actually in both the LVM, also XLA compilers. We look at inlining, we look at register allocation, we look at tensor graph in the XLA, and also auto sharding. So we actually evaluate the whole thing using the production compilers, also production binaries. And all of these results are basically for real, okay? Not just for small test cases. Actually, in some cases, we are also sort of seeing the benefits of using the latest AI models. Okay, when we started the project, so we were using the Gemini 2.5. So we are now able to improve the performance for inlining, but by leveraging a more recent AI model. So that's where we were able to break the ceiling. Okay. And we are also looking at different ways of designing the compiler optimizations. So if you think about the current compiler design, right, especially compiler optimizations, it's basically a fixed sequence of compiler heuristic passes, right? Again, those are designed by human, and those run on CPU, largely in a single-threaded way. Okay, so that's where we are looking at, can we take a page from the modern machine learning pipeline, right? Where things are actually end-to-end differentiable. Okay, and also we got to use some of the differentiable and learnable cost models, right, to drive the optimization. So that's where we have been looking at these differentiable compiler optimizations. We have looked at several important classes of problems, including equality saturation, so which is basically built on E-graph. E-graph is becoming popular in the compiler domain. So with the E-graph, we are able to actually encode many graph transformations in a single, more compact representation, and then extract a more optimized version from that. So we actually published a paper last year at ASPLOS, so where we showed that we can actually extract the solution from E-graph, so in a differentiable way, and then we can run this on GPU. So this one actually won the best paper award at ASPLOS last year. The good news is that it's not just useful for equality saturation. We can also do graph coloring and also scheduling as well. So all in differential way, and this compiler optimization can actually run on the GPU and also TPU. Okay, just want to sort of summarize. I just talked about Allo, right, which is our effort to bring the accelerator design, also programming, under one roof. There are many benefits, right? So with this sort of grid-based abstraction, so we are able to improve the design abstraction for the accelerator generation, right? So that one becomes much more performant, also much more productive, and also we are actually working very hard to also try to automate the bring up of the compiler stack for these new accelerator instances. As the parting thought, I just want to sort of peek into the future a bit. Actually, this is where we are now. Right? We look at accelerator programming, accelerator design, also compiler construction. So everything is manual, right? Everything's manual. But most likely, right, with the improvement of the AI, right, so there are a lot of exciting effort, right, so in that domain. So most likely we are heading into a near future where the accelerator programming can be more or less automated. Okay. But I really think that the real big game changer is where we actually automate the whole thing, right? Not just the programming, but also the design and the compiler construction. That will really make this whole loop autonomous. So this will allow us to search the space in a much productive, in a much more exciting way. And I think there are actually a host of interesting research opportunity in this area, for EDA, for computer architecture, and also for programming languages and compilers. Okay. So with that, I just want to give credits, right, to the amazing students, also postdoc in my group. They actually did all the heavy lifting, right, behind all the work that I have just mentioned. I also, want to thank our collaborators and also sponsors for their tremendous help and support. Okay, with that, I'll stop here. Thank you very much for listening.